Welcome to the Kościuszko Foundation Collegium of Eminent Scientists lecture series. My name is Marek Skulimowski. I'm the President and Executive Director of the Kościuszko Foundation. And let me introduce our distinguished guest today, Professor Henryk Iwaniec, who is our keynote speaker today, honorary and eminent scientist. Dr. Hanna Chroboczek-Kelker, Kościuszko Foundation trustee, chair of the Collegium of Eminent Scientists of Polish Ancestry and Origin, and chair of the Casimir Funk Natural Sciences Award. Dr. Włodek Mandecki, Kościuszko Foundation trustee, and also, as I know, a part of the Casimir Funk committee, and our guest from Institute of Arts and Sciences of America, president of this institution, Dr. Robert Blobaum. Now let me ask Dr. Hanna Chroboczek-Kelker to say a few words about the Kościuszko Foundation Collegium of Eminent Scientists.
In the year 2012, the Kościuszko Foundation established the Collegium of Eminent Scientists of Polish Origin and Ancestry to recognize the accomplishments of Polish-American scientists. The Collegium was created by Dr. Zbigniew Darzyńkiewicz, a prominent scientist and a trustee of the Kościuszko Foundation. Dr. Darzyńkiewicz set out to create a prestigious organization of Polish-American scientists whose achievements deserve recognition. The organization was also created to provide a director of eminent scientists that could serve to further contacts and exchange between the countries. The Collegium now numbers 445 members, and the member number continues to grow. Among the members of the Collegium are 4 Nobel Prize laureates and many leaders from all areas of science. For instance, the famous so-called Polish School of Mathematics, founded a century ago by Stefan Banach and Stanisław Ułon, is represented in the Collegium by Henryk Iwaniec, whom we have the honor to hear from today, and other notable mathematicians, his brother, Tadeusz Iwaniec from Syracuse University, and to name 2 more, Krystyna Kuperberg from Auburn University and Lydia Filus from Northeastern Illinois University. I also have the honor to serve as the Polish Institute of Arts and Sciences of America, PIASA's chair of the Casimir Funk Natural Sciences Award Selection Committee. The Funk Award was established in 1995 and named for Casimir Funk, the discoverer of vitamins. The award honors and recognizes an outstanding natural scientist of Polish origin. Among the 14 award recipients are 4 Nobel Prize laureates and other esteemed scientists. Today, we add to the prestige of the Casimir Funk Award by recognizing Dr. Henryk Iwaniec, an outstanding mathematician of Polish origin. Both the Kościuszko Foundation Collegium of Eminent Scientists and the PIASA Casimir Funk Natural Sciences Award help to publicize the achievements of the illustrious members of the Polish-American scientific community, such as today's speaker, esteemed mathematician, Dr. Henryk Iwaniec.
Thank you so much. And now let me introduce Dr. Robert Blobaum to say a few words about the award.
Thank you, President Skulimowski. Please allow me to also thank the Kościuszko Foundation for providing this virtual platform for today's event. The Polish Institute of Arts and Sciences of America, which is an organization that goes back to the Second World War, inaugurated its awards in history, the humanities, social sciences, natural sciences, and applied sciences in 1995 to honor distinguished scholars and scientists for their outstanding achievements. The awards, fittingly enough, are named after the Institute's founders in some cases and its historically most distinguished members in others. Each year, the award committees consider candidates in each of these categories, with their recipients announced at the beginning of the following year. Our practice has been to formally present these awards to our recipients in person at our annual meetings in June, at least to those who are able to attend them. Well, as we know, COVID has affected more than one best laid conference plan. And this is why I'm so grateful to the Kościuszko Foundation for providing the Polish Institute with this opportunity to recognize Professor Henryk Iwaniec, our Kazimierz Funk Award recipient, in the presence of his peers in the Kościuszko Foundation's Collegium of Eminent Scientists. Though I may not be among those peers as president of the Polish Institute, maybe I should say that I'm a historian, so Professor Iwaniec is providing a bit of history, I guess, especially for me. But I am sincerely honored to be part of this event. So as Hanna said, the Funk Award is named after the famous Polish biochemist who is generally credited with being among the first to formulate the concept of vitamins. And as I think she also intimated, the nominee should have contributed in a major way to scientific research and be widely recognized. And she has told us that there have been 4 previous Funk Award winners who have also been Nobel laureates. Raoul Hoffmann in chemistry, Frank Wilczek in physics, Andrew Schally in medicine, and our 2019 Funk Award winner recipient, Jack Szostak, who shared with 2 collaborators the 2009 Nobel Prize in physiology or medicine. So joining this truly distinguished company of Funk Award winners is our 2020 recipient, Professor Iwaniec. Before I turn the screen back over to President Skulimowski, I also wish to thank those who have rendered many years of service to our Science Award Committee. Dr. Wodek Mandecki, whom we will hear from soon, Dr. Hanna Hrabowczyk-Kilker is chair of the Kazimierz Funk Natural Sciences Award Committee, and the late Dr. Zbigniew Darzyńkiewicz, the moving spirit behind the Collegium of Eminent Scientists. Thank you.
Thank you, Mr. President. And Dr. Mandecki, now the floor is yours. Please introduce Professor Henryk Iwaniec.
Today's lecture by Dr. Henryk Iwaniec is a real treat. Dr. Iwaniec, the recipient of the Piazza Funk Award, is not only one of the most prominent Polish-American scientists, but one of the most renowned academicians in the world. And I hope this brief introduction will remind you of that. Currently, Dr. Iwaniec is a distinguished professor of mathematics at Rutgers University in New Brunswick, New Jersey, some 30 miles southwest from New York City. The field of mathematics to which Dr. Iwaniec devoted his career is number theory. I am sure we will hear a lot about number theory later today, but at this time, I would like to highlight why it is so important. Number theory is important because it deals with the most fundamental concept in the most fundamental discipline of all sciences, mathematics. And that concept is the concept of a number. By that I mean the regular number, like 1, 2, 3, 4. And you may be surprised by what I am saying because this seems to be so simple. But This is the subject matter of discussions by philosophers. 200 years ago, Leopold Kronecker wrote, "God made integers, all else is the work of man." And number theory involves many complex tools, computational or logical, many theorems, which appearance or formulation may appear simple. However, a proof of which may take many pages and years sometimes to derive. Dr. Iwaniec specializes in this type of studies. Dr. Iwaniec was born and raised in Poland. From early years, he exhibited great talent to mathematics. He won a mathematics Olympiad in Poland, which is a very tough competition for high school students. In college, that was University of Warsaw, he made a mark by writing and defending his Ph.D. thesis before entering graduate school, for which and for his master thesis, he got 2 awards. At a very early age, he was elected the member of Polish Academy of Sciences, which is a very prestigious academic title in Poland. He emigrated to the US in 1983, right after martial law was lifted in Poland. In the US, Dr. Iwaniec got a job right away in what many would call a dream place for an academician, and that was the Institute for Advanced Study in Princeton, New Jersey, which is the same place where Albert Einstein spent many years, a bit like earlier. Dr. Iwaniec will be speaking to you from a place that's about 10 miles away from the Institute. Currently, he is a distinguished professor of mathematics at the Department of Mathematics at Rutgers. He has a very special position, the New Jersey State Professor of Mathematics, that has allowed him to devote time to research. This is where he is working right now. He published over 150 papers in many mathematical journals. Dr. Iwaniec has received many prestigious awards for his work in number theory. I listed some of them on this slide, and let me go over some of the awards. Perhaps the most significant award of all was the Shaw Prize. The award was established by a wealthy businessman from Hong Kong, Mr. Run Shaw, in 2002. Dr. Iwaniec received it for introduction and development of fundamental tools in number theory and solving some long-standing classical problems. The award, it's worth noting, has the monetary value similar to that of the Nobel Prize. I will show a movie clip from the Shaw Prize award ceremony in a minute or two, but let me continue about the awards. Dr. Iwaniec received the Cole Prize in number theory for his fundamental contribution to analytic number theory by American Mathematical Society. When I spoke with Dr. Iwaniec, he expressed his appreciation for the awards received from institutions in Poland. This includes, in particular, the Banach Medal, for which he got for the fundamental contributions to analytic number theory from the Polish Mathematical Society. We will move now to perhaps the lighter side, perhaps humorous. To begin with, I would like to say that the Polish community in New Jersey did congratulate Dr. Iwaniec right after he had received the Shaw Prize. That was in 2015. He got a statuette. Let's see. He got a statuette and a lot of applause from the group of people from New Jersey. He and others were also treated with a very special cake. which had a mathematical formula written on top of it. And this formula was related to some of the work for which Dr. Iwaniec received certain awards. You already heard the name of Dr. Iwaniec's brother, Tadeusz, but you probably didn't know they both play guitar. I think having a distinguished mathematician as a brother, identical twin brother, brings a questions of genetic basis for mathematical skills. That would be a lovely topic for a question or two. The other pastime activity is travel. Here you see Dr. Iwaniec under an arch. Some of you may recognize that this is the delicate arch at the Arches National Park, Utah. I am the one who took the photograph. Dr. Iwaniec enjoys photography too. And here you see Dr. Iwaniec with his gear taking a picture in a beautiful surroundings, also in Utah. Dr. Iwaniec is surrounded by art. The art is painted by his wife, Kasia, who is an award-winning oil painter, situated in front of her painting. And finally, the highlight of this laudation, the promised movie clip from the Shaw Prize Award ceremony. The event took place in 2015.
Let us welcome the Shaw Laureates in Mathematical Sciences 2015. This year, there are 2 Shaw Laureates. Firstly, Professor Gerd Felting, please. And then Professor Henryk Iwaniec, please.
Well, Dr. Iwaniec, we all wish you best of health, many professional successes, many theorems to prove, and many additional awards. Dr. Blobaum.
Thank you, Wojtek. Well, now as president of the Polish Institute of Arts and Sciences of America, I'm deeply honored to officially and virtually present to Professor Henryk Iwaniec of Rutgers University the 2020 Casimir Natural Sciences Award in recognition of his outstanding research contributions to the discipline of mathematics. I also want to thank Professor Iwaniec for generously gifting the monetary value of his Funk Award to Piazza's Alfred Yuzikowski Memorial Library. So, Professor Iwaniec, congratulations and thank you. Professor Iwaniec will now share with us a few remarks of his own, followed by his lecture, mathematical concepts, some research questions, and just for me, a bit of history.
Each year, the Kościuszko Foundation Collegium of Eminent Scientists of Polish origin and ancestry recognizes individuals of outstanding accomplishment, whom we invite to present a lecture at the Kościuszko Foundation in New York, or as during the pandemic, to participate in a webinar. These lectures organized by the Collegium have been greatly appreciated by those attending, and they serve the goal of the Collegium to publicize the achievements of the Polish-American scientists. The inaugural lecture of this series was delivered by Nobel Prize laureate, Dr. Roald Hoffmann, a chemist, a poet, and a writer. His lecture set an awe-inspiring, wonderful beginning for this lecture series. We had the pleasure already to hear from Wojciech Mandecki the fascinating story of Dr. Henryk Iwaniec's accomplishments and about the many prestigious awards and honors he received. Today's event is the first in the Collegium lecture series that is dedicated to mathematics. We all look forward to being introduced to the language and ideas of modern mathematics, especially since the lecture style should make it accessible to general audience. Today, it is my pleasure to welcome our distinguished speaker, Dr. Henryk Iwaniec, Professor of Mathematics at Rutgers University, a member of the Collegium of the Eminent Scientists of the Polish origin and ancestry, and a recipient of the Casimir Natural Sciences Award for the year 2020.
Thank you very much for this very extensive, overwhelming introduction. I'm just speechless. I don't know what to say. Yes, thank you, Wojciech, for very elaborate introduction. Dr. Robert Blobaum for equally overwhelming introduction, etc. So let me say just briefly that I'm delighted to receive the Casimir Award and to join this group of distinguished recipients. It is particularly precious for me because it refers to my Polish origin, Polish heritage. I thank the committee of the Polish Institute of Academy of Sciences of America, of Art and Sciences of America, for just finding me in the crowd of very remarkable scholars in the USA with Polish connection. I also like to thank the Kościuszko Foundation for having me today to speak about mathematics, my beloved subject, my life. So thank you very much for having me and for all these rewards. And let me go to business. So let me talk about mathematics. Okay. So what is mathematics? For many of us, of people, it brings some scary memory from school. Particularly among students, the fear of mathematics is just unbelievable. Yeah. Right. There are reasons for it. Maybe one is that mathematics is pretty abstract subject, no shape like physics, biology, chemistry, medicine, etc. It's really abstract. But maybe other reason is very bad teaching. And I think, let me say something about my own experience. I remember going back home and the immigration officer was curious to know what I'm doing for living in USA. So I said that I do mathematics and research and teaching. He immediately responded, I would say with some proudly, that he was very bad in mathematics. this is typical reaction, even among educated people. I mean, the prejudice to mathematics. I think it's unfair, and it shouldn't be there. Because once you learn concepts of mathematics and its beauty and nice effects, aesthetic, you really must like it. There's no way back once you learn this. And mathematics is like life, like love. It's pretty personal and intimate. It can be complicated, nevertheless. So let me just tell you a short story about teaching in mathematics. A famous mathematician named Gelfand, Israel Gelfand, who is very well recognized for his contribution to pure mathematics, really giant of 20th century. He was also recognized for his passion to education on all possible levels, elementaries, high school, and college education. So immediately when he immigrated to the United States, he was asked by a reporter from some public newspaper to explain why it is so that that people don't like mathematics. I mean, what's wrong with teaching of mathematics? He said, well, it's a matter of approach. Well, can you clear your point, please? So, okay, let's, for example, do this. Ask a pedestrian on Moscow streets, which number is larger, 2/3 or 3/5? Many people would have hard time to figure it out. But you may ask the same question slightly differently. Say, ask, what do you prefer? What would you choose? 2 bottles of vodka for 3 people or 3 bottles of vodka for 5 people? I bet no problem of finding the correct number. So this is a joke that I know directly from Professor Gelfand. He was actually, his office was in Rutgers vis-a-vis mine, so I had a lot of contact with him. Very nice person. But that's not the subject of my lecture here. So let's try to be a little bit serious, right? Okay. So let me. Okay. Yeah. So. I think the popular perception of mathematics is just counting, right? Counting objects, time, volumes, measuring things, counting. That's early occupation of people with mathematics. And already there, long ago, people start thinking abstractly. They associate symbols, numbers with counting. They, finger counting was just adding fingers and etc. But people start really thinking abstractly. So they just start using operations on numbers, adding, subtracting, dividing, and subtract. Got negative numbers sometimes. Oh, they got 0. Oh, that was a problem for quite a while of understanding the concept of 0. I mean, the cardinality of nothing. It was really philosophical a problem. That's long ago. I think everybody today comprehend what this number stands for. And yeah, okay, this famous quotation of Kronecker was already said here, so I don't repeat. But this is lovely. It is related to what I'm saying in a moment of modern models of mathematics. We start from something very fundamental without any questions, like integers. Kronecker said that God made the integers, or else is the work of man. Yes and no. Let's see how we explain that. So integers, whole numbers, were not sufficient for expressed things in life. They're not, people introduced fractions, rational numbers, and that was pretty large set. But still both integers and rational numbers are countable. So in a sense, they are not much larger, the set of rational numbers versus integers. But then people, even though you can approximate many things with rational numbers, it was not good enough to pursue pure science. Sometimes you need really exact answers. So people introduce real numbers as limits of sequences of rational numbers. Like square root of 2, for example, pi, you see some algebraic numbers are transcendental numbers. By the way, I'll be using certain, terminology of mathematics, and I know I'm fully aware that many of you here listening don't know that terminology, but I hope at least you get some impression what it is. Never mind definitions. Okay, so so real numbers were introduced, interesting enough, pretty late. In 19th century, it was pretty late. It was introduced. I mean, the correct, precise, rigorous definition of real numbers. Real numbers were already, in operational, of human being long ago. But definition, precise, mathematical, with rigor, was introduced in 19th century only by Cauchy and Dedekind. Well, not everything would be, possible to study with tools of using real numbers. People for analysis particularly had to extend it further. Real numbers, by the way, is much larger set than rational numbers or integers. I come to this issue a bit later. The continuum of them, it's much bigger set. Even though both are infinite sets, there is a distinction of cardinalities in some sense. Yeah. So the real numbers are still not sufficient. So people will start adding something extra, like imaginary numbers, like I, which is a square root of -1, and put numbers in coordinates, so complex numbers. And these were really complete set, sufficient for doing modern analysis. Complex numbers are really the ultimate object of current analysis, so to speak. Certain operations in numbers were not commutative, and that means operations depends on the order of execution. Like A plus B is not A times B is not necessarily B plus times A in certain systems. For example, Hamiltonian quaternions, which are really four-dimensional, is an example. And current knowledge of current science really requires non-commutative systems, like particular in many dimensions, like representation theory. So it's not just a caprice or something that people invent. It's really something that is needed, very needed, right? But I will not talk about it. Arithmetic is one of the first theories of mathematics. It deals with and number theory, which is extension of arithmetic by tools from much larger collection of tools, particular analysis. That's what a number theory is versus arithmetic. But the fundamental result, the theorem of arithmetic tells you that every positive integer is a product of prime powers. Unique product. That's Euclid in 300 BC, more or less, who first systematized, knowledge of mathematics, first of all geometry. But let me continue about arithmetic. So prime numbers were already, in focus. What are these prime numbers? They are just numbers which are divisible by themselves and by 1 only, no other divisors. So it's like elementary particles in the theory of matter, like in physics. The arithmetic is built out of prime numbers. And Euclid was first to, Euclid, no, I'm not sure if it was first, but he produced a proof that there are infinitely many prime numbers. This is wonderful, moment of mathematics, because it introduced the idea of proving by contradiction. So there are infinitely many primes, but still people like to have the largest prime, the largest that you can write down or memorize. So here is the one I figure out from internet. This is the 3 years ago number which has 25 million digits. Right. I don't think you can memorize all these digits. But I challenge you to memorize all the digits in binary system of that number. It's a joke. Please try it. All right. So, but seriously enough, distribution of prime numbers are the fundamental matter, in number theory, and a bit also in mathematics, I would say. So, distribution of primes. There are plenty of them, but we don't know how regularly are they distributed. They really behave like chaotic, systems, etc. And so if pi of x denotes the number of primes up to x, we know how many of primes are there, more or less. Statistically, it's about x over log x. So zero density, but not that little. I mean, only by logarithm x less than x, number of prime numbers. This is fundamental theorem of number theory, prime number theorem. The asymptotic formula for number of primes up to x. And equivalently, if you put primes in increasing order, the nth prime behaves like n log n asymptotically. Again, I realize that many of you don't capture that. Those who are not mathematicians, but I hope you are still convey some impressions. So let me continue. This is the Riemann hypothesis. The one maybe the greatest open unsolved problem in modern mathematics. That's the Riemann hypothesis. It originally was stated in 1859 by Bernhard Riemann in terms of some complex valued function and the distribution of its zeros, but that would be too abstract to talk. So let me just give you equivalent statement of that hypothesis, how the prime numbers are distributed. There is a much more precise formula than x over log x for the pi of x, and the precision, the error term in this approximation is about square root of x. That's the content of the Riemann hypothesis expressed, in elementary terms, but maybe not so spectacular statement, but that's what it is. It's the greatest open problem in mathematics that is not solved today. There's a price for solving this, $1 million. Yeah, minus taxes. Right. And right. So this is the Riemann hypothesis. And the other problems about prime numbers, how are they distributed? The gaps can be large or small gaps. There's a conjecture still open, also deep, twin prime conjectures saying that there are infinitely many pairs of primes that are distanced by exactly by 2. So these are twin prime conjectures. And here examples of twins 3, 5, 5, 7, 29, 31, etc. Conjecture says there are infinitely many of these. It's hopeless conjecture to prove by tools available today. All right, let's go now to geometry. This is the really beginning of mathematics with Euclid. Geometry deals with shapes, positions, dimensions, and other things like this. Everybody intuitively know what geometry is. In high school, you know some theorems, beautiful properties of some figures, geometry of figures like Pythagoras theorem, right? But Euclid was the first who systematized, compiled known great theorems of geometry into a system of axioms. He published this in Monumental Elements, which consists of 13 books. Most of it deals with geometry, some about arithmetic as well. Right? And what are the axioms? The axioms are just the list of facts, of propositions, which are not subject to verification. They are given as absolute truth without checking, but they are so simple and obvious taken from observations that really people don't object. They take it. The idea of axiomatization is that that once you set these axioms as absolute truth, God-given, so to speak, right now, then the rest comes out by logic, by deduction using logic. It has not much to do with real world. You see, so in that sense, you may say that mathematics is the product of people's mind. Once you set the axioms like that, like art. Well, I don't completely, share this viewpoint, and I will explain myself later in a different, maybe better context somehow. So it is true that it is either pure, we create mathematics or we discover. That is still a question that we people are divided about, this viewpoint. Anyway, axioms in order to be really good should be coherent, cannot really produce contradictions. They should be complete in a sense that this axiom should be sufficient by way of logic, to deduce a lot of properties of theorems, new theorems that we just like or want to describe as real things happening in the world. So also there should be minimalistic in a way. That means to say you should not put to axioms something redundant, something that is dispensable. You see, like that. So this is the idea of axiomatization, which is now a common practice in creating new theorems in mathematics in many other directions. Right. There is a big problem about these axioms because some people, the Euclid axioms of geometry consisted of 5 postulates. And the 5th one, called parallel postulate, was questioned. People started wanted to deduce it from the other axioms or to actually prove that it is false. And what this says, it says very simple, right? If you have a line and point off, not on the line, there's exactly one line through this point which do not intersect the given line. That is parallel, in other words, like that. Obvious for us, right? But people with imagination had some question and tried to argue that this may not be always true. See, equivalently, you may say that this postulate tells you that the sum of angles of triangles are equal pi, when two right angles, 180 degrees. We know it from school, right? And just about 200 years ago, less than that, right? People start thinking seriously about removing this axiom and replacing by other. So hyperbolic geometry was created by assumption that there are infinitely many parallel lines. So there are lots of models of this hyperbolic geometry known in literature. I like the so-called Poincare model. I really have to rush. Cannot go into details. You don't know. I don't know what if I'm clear enough, what does it mean a model? But let's postpone it or put it just unclear. So Poincare model of hyperbolic geometry is the points are in the upper half plane. So the model is just a Euclidean plane, but points are in the upper half plane only. And there is a different metric than that is known, from Euclid geometry, hyperbolic metrics, and then it gives you concept of straight lines. Segments lines are just simply connecting points in the shortest possible way. That's how the geodesic line is defined, and happens they are not straight lines. The closest the distances between points are along some other curves, like half circles orthogonal to the real line. That's the geodesic lines in Poincare model of hyperbolic geometry. Triangles looks the same, but both sides are just sections of this circles. Angles are the same. And that's a hyperbolic. This is a hyperbolic triangle. What is curious here that sums of angles of triangle is strictly less than pi, not equal to pi, and this is because of the curvature. This is so-called negative curvature. The space is bent. It's not just flat like that. Gauss find out what is the deficit. The deficit is just the difference, pi minus alpha and beta, is what? It's just the area of the triangle. It's a beautiful formula in hyperbolic geometry. And one thing you have to notice, that area of a triangle does not depend on the sides of a triangle, on the angles, not like in the Euclidean space here. This is because of the curvature. Other thing that is curious, I have no time to talk about that, how the points are distributed, they measure the area, hyperbolic area of a domain in hyperbolic space is mostly concentrated along the boundary. So it makes harmonic analysis, much harder there than in Euclidean, but it's much more powerful tool. So believe it or not, even this kind of geometry, harmonic analysis, automorphic forms by domain, is used to study prime numbers. But of course, most people know that spaces with negative curvature use in general relativity, Einstein theory, etc. It's a real thing. Let me speed up because I don't have much time to be more precise. Unless somebody in question asks me, I would be delighted to talk more about this, but let's go further. The philosophy, logic, and set theory. I'm not so sure if philosophy is mathematics, but logic and set theory, yes. Okay. So one of the questions about arithmetic is the completeness. The completeness, that means the axioms of arithmetic are sufficient to do everything what we dream to get out of it, right, so to speak. Right. So well, first of all, we have to axiomatize arithmetic. So it was, I think, first serious axiomatization of arithmetic was done by Peano, who introduced mathematical induction, for example. Right, and Hilbert, a giant of mathematics, in the history of mathematics, David Hilbert, represented this formalism. He was a dreamer. He really wanted to make a set of axioms which would be sufficient for all mathematics, just set of axioms for all mathematics. And it was naive in a sense. It's strange for me to say it was naive when the giant of mathematics tried to do it, David Hilbert. But anyway, his wishful goal was demolished by Kurt Gödel, in 1931, who published a paper about Incompleteness Theorem. Kurt Gödel, I think, is the #1 logician of all time in the history of mathematics. I will talk about #2 in a moment. So he what it is, roughly speaking, whether it's, I mean, I understand you may not really understand my words. These are really loose statement. It says that consistent formal systems, not only just axiom, you have to also have proper language for it, in which all these elementary operations can be done within arithmetic. It is necessarily incomplete. There is no such thing like complete system. In his sense, precise sense, what this means, it's incomplete. It's nothing wrong, it's just incomplete. That means you can formulate a sentence, you can formulate a statement which, in the language of your system, which cannot be proved or disproved. Neither proved nor disproved. That's a huge statement of incompleteness theorem of Kurt Gödel. So the dream of Hilbert was crushed. Okay, and Polish school of logic has essential contribution to the history of the subject, and I come to this in a moment later, if time permits. And but very weird thing happens in axiomatic theory, set theory. Set theory was created by George Cantor based on this logic that you know what a set are. Right? Sets consist, have elements, you can add, you can make a union of sets, you can intersect sets, this kind of things, right? And axiomatic theory or set theory was I mean, many attempts were done, but the most acclaimed, system is by Zermelo Frenkel and extended soon by so-called axiom of choice. Oh, it's almost embarrassing to talk about it because these axioms are so obvious. Why people were worried? Why they worry about it? You know what this says? If you have a collection of non-empty sets, let's say infinite collection because it's trivial for finite collection, infinite collection of non-empty sets, you can pick up exactly one element from each set. I mean, this goes without saying, right? It's so obvious. Well, luckily for mathematicians, it was not obvious. The point is that you don't have a function of choice choosing these elements. Let me give you quickly, I don't know if I have time for it, right? Quickly how this was illustrated by Bertrand Russell, sort of a joke, right? If you have a collection of infinite collection of shoes, you can select one shoe from each set. For example, a shoe for the left foot, right? But if you have infinite collection of socks, you have no way to select one from each collection. Okay. So that's the difference. That's the essence of axiom of choice. But it is so obvious in a way that people accept that. When you accept that, really, really strange things happens. By way of logic, you can prove something unbelievable. Here is one example, Banach-Tarski Paradox. What it says, any solid ball can be decomposed into a finite number of disjoint pieces. And then out of these pieces, you reassemble two copies of the same original ball. The same ones, no holes, no empty spaces, no adding any points, just exactly the same ones. But more importantly, this oh my God, I should really. More importantly, the composition is such that these pieces are you assemble these pieces with rigid motions by rotating on or pushing them forward and backwards. You don't change the shape. You don't squeeze them. You don't contract anyway, just isometrically, so to speak. This is really a paradox. You get two balls out of one, identical. Imagine these balls are out of gold. You would produce gold from air, you see, like that. Well, the point was, of course, that the measure theory, you know, the axiom of choice tells you shows you the existence of sets for which you cannot attach measure, the volume, the area, etc., something like that. So this is the paradox. And one of the other consequences of paradox of this axiom of choice is continuum hypothesis. I mentioned that real numbers are larger set than integers, and in some sense much larger. They are still both are infinite, but one is countable, the other is uncountable set. So there is a hypothesis that there is nothing between, that in terms of this infinite cardinalities. So that's a continuum hypothesis. Means and in 1933, Paul Cohen showed that continuous hypothesis is independent of the axiom of Thurman and axiom of choice. Independent. That means what? You either can prove that, you cannot prove it or refute it, I mean, or to disprove it. So you can accept it or not. So then you have two different worlds, you know, and you can continue your way and depart from your friend who accept it and you reject it. It's up to you to accept that. This is mathematical statement. It's not just simply a loose, you know, choice. Yeah, mathematical statement within the axioms of that has been proposed. By the way, Paul Cohen was a student of Antoni Zygmunt, who is Polish mathematician representing Warsaw School of Mathematics, and really one of the greatest in his time analysts, you know, harmonic analysis, Fourier series. He immigrated to Chicago. Paul Cohen was his student. And also other people. Józef Marcinkiewicz was also a student of Zygmunt. I don't really have much time to talk about these individuals. They're really nice people. I was fortunate to meet Cohen personally and actually know him personally. I even lived in his house for 2 weeks. A wonderful fellow. So he proved that the continuous hypothesis solved the problem. It's just independent of the axioms. There are other you know, really weird things coming from this kind of axioms in mathematics. One of sources for ineffective results is this principle of explosion, that anything follows from false assumption. So you can prove anything once you assume something false at the beginning of it. But there is no time to talk about it unless you ask me some question to give an example of ineffective results. But anyway, so I don't have much time to talk about Polish School of Mathematics. But one group of researchers, the Warsaw School of Logic, is really powerful. You know, Wolasiewicz, Tarski. Tarski is considered as second after Gödel logician of the world of all time. You know, he is working model theory, mathematics. Łukasiewicz earlier, you know, he introduced Polish notation. This terminology still is known in literature. More or less, it means he found a logical notation which avoids using brackets. etc. Now, other great giants of Polish school of logic were Mostowski, Andrzej Mostowski, Rashowa, Helena Rashowa, and few other things, Jan Michelski, for example, etc. And I have no time to talk about other, schools of Polish mathematics like Krakow or Lwów, Warsaw also. Maybe if time permits, I will make a little bit more comments. Let me change a little bit the subject. Polish mathematics, well, in mathematics as whole, is a really dominating area is analysis and topology. Topology is studying, things that look the same when after the continuous deformation. For example, in topology, a cup of coffee with a handle is the same thing like a donut, topologically. But I don't propose to verify this by tasting. I think donuts are nicer than, don't crush with your teeth your cup of coffee, but the cup of coffee and donuts are the same. That's what topology is about. So one of the questions in topology is a fixed point problem, which means that if you have a map of topological space that which is continuous or satisfies certain other conditions, there is a point that is fixed point. Right. So started by Brouwer, the Dutch mathematician, who was actually more known as a philosopher of intuitionism, but he did the fixed point business. But Polish school was really, really powerful in this. And so Polish contribution to fixed point theory is Banach, Knaster, Tarski, again, Tarski is everywhere, Rylnardzewski, and Julius Schauder. Schauder, tragic figure in Polish mathematics, didn't live long. Was just executed by Gestapo. And so let me just give you another beautiful application of fixed point theorem. This is Borsuk-Ulam theorem about antipodal points. If you have a continuous transformation of a sphere is a surface of a ball, or and one-dimensional, that's just simply a circle. Two-dimensional would be a surface of a sphere. If you have such a map which is continuous without breaking, things that transforms that surface into Euclidean space, then there exists a point such that f of minus x is f of x. Minus f of x here depicts mathematically the antipodal point to x. That's a theorem, mathematically stated, but if you don't like mathematical formulas, okay, here is the corollary in a human language. You see that the corollary first, anytime there is a pair of antipodal points on the Earth's equator with the same temperature. Isn't that nice? Of course, we assume the temperature as a function is continuous. Why not, right? That's in dimension 1, n1, s1, that's just a circle, that's an equator, right? Take the dimension 2, then it's a sphere, right? Then you consider points on Earth's surface. Then you can find pair of antipodal points. I mean, the point that are most distanced on the surface of the Earth, So you can find the theorem says there are 2 points, antipodal points, where at any given time you have the same temperature and barometric pressure. 2 parameters equal. That is a really practical result, I think. Right? Okay. Anyway, great. And I don't have much time to talk even more, so let me just make a conclusion, then save maybe some time for discussion or maybe showing some pictures, photographs. So let me conclude with my own characterization of our species of mathematicians. So mathematicians love abstract thinking. They can identify equivalent structures. Like I said, the cup of coffee with handle, and the donuts are the same for mathematicians, right? You know, they can generalize things. You know, they can see more structures in general terms, and they see analogy between different events. So that's what mathematicians' life is all about. How they visualize, how they live in their own space by this. So let me end with two interesting statements. One given by Henri Poincare, a French mathematician. I think he's justly considered as second greatest mathematician ever lived on planet, Henri Poincare. And he said, mathematics is the art of giving the same name to different things. Well, yeah, I see Eva is laughing, so it is laughable, right? But I think it's a very deep statement. Think about it, please. Okay, right? Think about it. It's not trivial. Okay. And now the final the statement of number one mathematician of all time, Carl Friedrich Gauss. He said this: mathematics is the queen of sciences, and number theory is the queen of mathematics. I like it, because number theory is my domain. All right, so thank you for your attention. I have some pictures to show if time permits. That depends on the moderator. Thank you. So this is these are this collection of photographs of Polish mathematicians. And let me make a quick comments about some, of course, not complete. There are thousands of us around the world. You see, so Sierpiński first, is famous, very broad mathematician. He is shown in some cover of Intelligencer. In the background is his famous fractals. Sierpiński carpets and other things like this. But he was really interested also in number theory in his life, but I come to this in a moment later. Next one, oops, no, I shouldn't do that. Yeah, okay. Next one is Stanisław Ulam. Here is Otto Nikodem on the left, Stefan Banach is on the right, and in the middle is the future of Polish mathematician. And he again repeated, these are pictures given to me by Hanna Kelker. Thank you very much. Nice picture. So these two mathematicians, Nikodem and Banach, were discovered by Steinhaus, when walking on the plant in Krakow, and they were sitting on the bench and talking about Lebesgue measure. He heard of them, and then Steinhaus, this guy here on the right, he used to say that his greatest discovery of mathematics was Stefan Banach. So this is the history. That's how these two gentlemen sitting on the bench. Next one is Kazimis Kuratovsky. He is again Stefan Banach, the really founder of function analysis. Modern function analysis is he's founder of it. Function analysis, yeah. He is Alfred Tarski, number two logician of all time in history of mathematics. I think it's fair to say so. After Kurt Gödel, he is Andrzej Mostowski. I know him. I attended his classes in Warsaw. He was talking about history mathematics, of course, logic, but first of all, and I think like that. Then, he is this is in the middle. Antoni Zygmunt, who is from Chicago. Great analyst who educated many people like Paul Cohen, and and many other people. First of all, he knew personally Józef Marcinkiewicz. You should probably read it on the internet about the story. I don't think I should talk about this here. Helena Rasiowa is a Polish logician. I also knew her. I met her personally. Hugo Steinhaus. I was fortunate to see him once or two times. And here is Józef Marcinkiewicz. He died tragically. Well, tragically, he was murdered by NKWD in Starobielsk in a massacre of Katyn. His great theorem about interpolation is still valid today. Here, Karol Borsuk, expert in geometry and topology, theory of contracts, something like that. Oh, this is this one here. This building is Scottish restaurant. That's where Polish mathematics was flourishing. I mean, solid Polish mathematics with proofs. You know what proof is? Proof is 50% of alcohol. This is a copy of Scottish book, famous one. Again, the bench when Otto Nikodem and Stefan Banach are talking about Lebesgue measures from Krakow. Okay, Stanisław Mazur here, one of the Lwów school creators. And again, Wacław Sierpiński. Sierpiński was really ambassador of Polish mathematics after Second World War. You know, very, very recognized. He worked in logic, but particularly, or mostly not much logic, but really set theory and topology and cardinal numbers. In his later in his life, he spent a lot of time for number theory. Actually, his PhD thesis was in number theory. He was a student of Voronoi. Yeah. Anyway, so I was unfortunate that I don't remember meeting him, even though he was still alive in Warsaw, and I was already doing number theory. So I don't recall meeting him personally. He was already quite sick when he died in '69. Professor Schinzel, my thesis advisor, was a student of Sierpiński. So I think I have right to say that Sierpiński is my mathematical grandpa. Well, thank you. So let me go to questions now, right?
First of all, I would like to thank you on behalf of the president who had to leave, and I believe all of us. Thank you very much for this wonderful, very informative, interesting, and entertaining lecture on math. I can say for sure, but it's very probable that it was the first lecture on mathematical concepts that was delivered for the Kościuszko Foundation, definitely in its most recent history. And I know that this is not a regular lecture that you deliver to your students or other fellow mathematicians, and it took some extra time from your schedule to prepare a lecture for address for a general audience. And for that, we owe you a special vote of thanks. So thank you very much. And now let me go to the questions from our audience. By the way, we had a nearly full house. Nearly 100 people attended this lecture, which is a wonderful turnout. So we have a lecture. Okay, we have a question from Mr. Andrzej Kobisz. Do you consider Poincare greater than Newton and Archimedes?
Yeah. In a way, it's a meaningless question, because everyone here on the list are number one. You see Newton in modern era, Archimedes, of course. Archimedes was not really a mathematician, you know, but my soul is closer to contemporary science and mathematics. So that's why I think Poincare is number two, Henri Poincare. Of course, Newton in physics is considered number one or something like that. So answering the question, I would say I don't change my mind. Yes, Poincare first, and Newton and Archimedes are just in a different category. Yeah.
Okay, another question from Olivia Jesnach. What are other hot topics in mathematics despite Riemann hypothesis?
Yeah, Riemann hypothesis is considered as the greatest unsolved problems, and because of my interest in number theory, no surprise that I agree with this. And of course, there are many unsolved problems in many other branches of mathematics. I didn't mention topology, I didn't mention cryptography, statistics, combinatorics, probability, dynamical systems, and many other things. And they, each of them have open problems, fascinating and important. So, so again, it's personal. I just have some, emotion to it, and that's why I say that the distribution of prime numbers is the most important one. Luckily, even people not in the subject are fascinated by distribution of prime numbers. So I think for even purely human curiosity, the Riemann hypothesis is very attractive. To give an example of other unsolved problems, there's so many of them. I don't know which one to pick up. P and NP, that's something harder to describe. I mean, there are a list of unsolved problems given by David Hilbert in the Mathematical Congress in 1900s that supposedly was created to shape the future of mathematics. And some of these problems already were solved, some still are open. The Poincare conjecture that was recently solved by Perelman is one example, but it's just solved, a very interesting story, because he didn't accept that the greatest, awards for mathematicians in his age, the Fields Medal. Again, you can read this in media about him. So that was one problem. But there's other problems. It's hard to define for general public, like Swinnerton-Dyer conjecture about elliptic curves, for example. Something about differential equations, conjectures, and so I don't have a direct answer. What is the most? With other things, it really depends on your field. Of course, I could have endless number of unsolved problems in number theory.
I think that answer answers the question. Another question, Włodzimierz Kalat asks whether you could tell us few words about Roy's number, and that really needs to be few words because I see there are more other questions for you.
No, I actually expected that somebody would be asking me about cryptography, because number theory is applicable to cryptography. And it happens that my own work does not really touch that field, but prime numbers are present and very important and useful for creating public codes. factorization of numbers are used to create public codes in cryptography. But because I have a general view about what cryptography is, and not so much about whether this is numbers, primes, and like that. Well, yeah, everybody has the same view. What cryptography is, the philosophy of cryptography is that you have a process which is relatively easy to describe or to perform, but it's very, very, very difficult to reverse this. You see, so that's what you use. So but why it could be just any process in chemistry or in mother nature, other things like that. But why in cryptography use numbers? Because computers use numbers. You have to use tools to do that. So that's how number theory is used in cryptography. You see, it's not something very special, in my opinion. Let me make a little joke about the cryptography. I mean, so in 1970s, in the middle, there's a economic crisis in Poland. A food crisis, shortage of it, which was ridiculous. Poland was recognized as an exporter of food, producer of food. Agriculture was in good shape, but political system created this chaos. So there was a food crisis. Nothing, you couldn't buy even potatoes on the market. So somebody proposed the following solution: use vodka to transfer vodka to potatoes. See, so this is example of reverse technology, right? So somehow cryptography is like that. You can't really reverse the process because it is so complicated and it requires computers of incredible power that is not available today. So it's still valid cryptography. Okay. That's my answer.
Very good, thank you. Another participant, Stanisław Radziszewski. I believe you can
yes.
This question: is it valid to claim a proof was done by a computer?
Okay, yeah. There are temptations in mathematics to create computer assistant proofs. So I would accept a computer verifying our computations, but I don't like a future that computer will be creating new theorems and just be giving us the final statements, and we dogmatically would accept that this is true because computer said so. So if artificial intelligence is created, and I will be very unhappy actually. But computer assisting proofs, I do accept. So because of power of computing, speed and reliability, how verifying details by computer, that's okay. But the question was, does mathematics come from? Oh no, that's a different question. And that's my attitude towards computer. You see, I mean, if computer really is replace humans in creating mathematics, that'll be at the end of the world. Like computers completely removed people in chess game, for example, like that. So,
yes.
Yeah.
So we have a question from Patricia Brubel. Does mathematics come from logic, or does logic come from mathematics?
Right. Well, I think they are interrelated, that logic and mathematics, don't take it, somewhat formally, mathematics versus logic. I mean, logic was created in order to create very rigorous system to cultivate mathematics, and then mathematics use logic to express themselves. So I think the question, what comes first, or may be interesting for some people. I would like to know the answer of the person asking me too. But you know, I have some advantage that I don't ask unnecessary questions. I just do my beloved work, and I just watch what other people struggle in mathematics. Right? Yeah.
That's the right thing to do. Yes, selection. We have a question from Mr. Frederick Zimnoch, who, well, shares his thought with us about the things that you spoke for many. Okay, he said that he hasn't thought about the things you spoke for many years, and these things made him recall something that he always found fantastic. It's the Goldbach conjectures. He asked whether you could say a few words about it.
Well, Goldbach conjecture says that every sufficiently large even number is sum of two. It can be represented as sum of two primes. I don't think it has any implication for any applications, but it's a beautiful problem which stimulated the development of many branches of mathematics, and still is open problem not solved. So that's the value of such conjecture. We study conjecture by curiosity, and by doing that we develop new branches of mathematics. Yeah, so it's a difficult problem. Yeah.
Next comment from Basia Betancourt. Pani Basia, sorry if I misspelled your last name, but she says, thank you very much, Professor Iwaniec, for organizing this great presentation. And she asked whether where it will be available. So for this question, I can answer. We are making a recording of this webinar, and we will post it on the Foundation's website, and it will be on our YouTube channel. So we'll keep you posted also with our email communication. All right, the next question we do have. Okay, I believe the next question will be from Mr. Ryszard Czermiński, who asked, what is your take on uncanny applicability of mathematics to the physical world?
Well, definitely this is extremely connected. I mean, mathematics was inspired by physics, and physics was inspired by mathematics. I mean, mathematics is a language of expressing, properties, phenomena in the world in terms of equations, and so my quick answer to the very brief is just yes, they are interrelated. I mean, look for example the creation of non-Euclidean geometries is really inspired by physics. You see, the relativity theory today. I mean, even other things, in physics, were created, inspired, mathematics, like, well, dynamics, explaining this, created areas of mathematics, dynamical systems, ergodic theory, etc. These are inspired by physics. So there is no question that physics inspires. Mathematics is not only art. Mathematics is not only the real physical reality. It's both. Yeah.
Okay, thank you. I will switch momentarily to our different feature chat feature, where Dr. Mandecki asks how to improve teaching of mathematics, role of genes and genetics in acquiring mathematical skills.
Oh, it's very simple. Just bring candies to the class. No, I mean, it's a huge subject. That Wodek asked me this question.
Exactly. Yeah. He could have asked it himself, but thank you for
right.
following the suit.
No, there's a great attention to education in mathematics. American Mathematical Society is very much involved in education, in developing methods of education, etc. But I'm sorry, I just refuse to answer. It's just too, the subject is too broad. The example that Gelfand, I presented of Gelfand point was a joke. Don't do with bottles of vodka. Okay.
Okay, so let's return to our Q&A session. Alexei Muravitsky asks, what is your comment on the possibility that the last Fermat's theorem is not derivable in the format piano arithmetic? Thank you. I'm not sure whether, most likely
Arithmetic, I think he misspelled
arithmetic, yeah.
It's a great question, actually, because you see, last Fermat theorem was proved by Andre Wiles using automorphic forms, elliptic curves, and these forms live in hyperbolic space, you see, which was not known during period of Pierre Fermat. So one may ask if the proof is really legitimate. It uses the extension of mathematics by different geometries, right? So whether this is provable within piano or arithmetic, I never thought about it. Maybe there is answer somewhere in literature. I don't know, but it's a very good question. Because modern mathematics is extended by certain things that didn't exist in the past.
Thank you for the good question. And now we have a question from Vit Busha, who asks, who or what gave rise to the brilliant schools of mathematics in Poland in the early part of the 20th century?
A Scottish restaurant. I think that the Polish mathematics between the war, the Scottish, the Lvov period, was a nice, lucky, so to speak, moment, because when you create something new, the problem is not that something is new, whether it is accepted by the world, and whether it is so fundamental that it would have everlasting consequences. So the Polish school of functional analysis, created by Stefan Banach and of course Ulam and Steinhaus, Mazur, other people there, but first of all, of course, Banach, the concept of creating Banach space, I mean, vector space with norm, which is complete, it's not something super revelation. If you look at the other spaces that has been, introduced before, like Hilbert spaces, or etc. The point is that there was a fantastic balance about generality of, in terms of structure and being useful for things. Almost every reasonable space in mathematics is Banach space, etc. So in responding to the question, what created is somehow a good luck in a way, that what they were interested, of course, a talent and great mind, but on top of that was that what they created happened to be extremely fundamental. People in the world captured, they discover it very quickly and distribute it and develop further. The worst thing may happen, you invent something that nobody cares, you see, but that was not the case. You see, people in America wanted to bring Stefan Banach to the United States and some other, there's a famous stories about how von Neumann sent an assistant to go to Lvov to offer a job for Banach in US, and he with a check number 1, and then ask him write number of zeros, as many as you want. And Banach said there's no price for leaving, Poland. Yeah.
Thank you. Another question is from Mr. Ryszard Wawak. Does the fact that a statement can be formulated in the language of a mathematical theory, but cannot be proved or disproved within that theory, have philosophical implications outside mathematics?
I don't know. I never lived outside mathematics. I don't know.
That's the answer. Great. George Ditchen says, thank you very much for reminding us how important mathematics is and what great contributions Polish mathematicians have made, including you and your students, of course. It was a great pleasure to listen to your lecture. We are in full agreement. I concur. We both concur.
Absolutely.
Before we conclude, I see.
Thank you very much. That's my answer.
There is also a question from Lucia Cannon. She's asking about any recommendation of a book in English on the Polish School of Mathematics. Is there any? Can you recommend any?
I don't think there is really a full book about history of Polish mathematics or Polish mathematics. There are quite a number of books treating special issues, like that. The Scottish book was translated into English. I have a nice book about Stanisław Ulam that somebody sent to me. It was in English, and I even pick up. So there are some publications, but I don't recall any specific one. There are about Polish. I don't think it's a subject that people easily write. I mean, they write in articles, in journals, etc., but not really books. You see, yeah. But at least this is my take on it. Yeah. No,
Okay,
I'm answering to Lucia. This, please try to find on internet. You have infinite source of information about this. Just click Polish School of Mathematics. You find out fantastic, accounts of Polish mathematics in it. I can't make it. I cannot do justice by saying briefly a few words about it.
Okay, I think that among the Q&A questions and comments I think that the last questions from Roman Schneider, are you aware of any elementary proof of Thurman last theorem?
No, I don't. And I always tease with people when they ask me this question that one should really still try to find elementary proof. Even though proof once is given, you may think there is no point to do it, but I do not rule out there could be elementary proof, but based on psychology, that is to say, hundreds of years people tried to prove. They developed incredible theory. Algebraic number theory by Kronecker was created on this because of the attempt to prove last Fermat theorem. Based on that things, I guess it is impossible to find. People who have brains, they tried hard and they failed. So this would be my prejudice to try to prove Fermat elementary, but formally speaking, it's not ruled out. Yeah.
Okay. I can see just one last comment, but let's say Murawicki, who I believe refers to the literature, and he recommends, yes, Roman Murawski, The Philosophy of Mathematics and Logic in the 1920s and 1930s in Poland. I believe it's a
voila, yeah, very good. So
Thank
there
you.
is such thing, yeah.
Thank you very much.
Wonderful, wonderful. I have to read it. Yeah.
Thank you. So I believe that this comment would conclude our webinar today. I'm joining once again George Ditchin and who else? Anonymous attendee and Frederick Zimnoch and others who sent additional comments via Q&A feature, thanking for the wonderful and very informative presentation. Thank you on behalf of us all. Thank you very much. I also want to thank Professor Robert Blobaum, as well as Foundation's trustees. Let me switch the view to our gallery mode. Yes, Dr. Włodek Mandecki for absolutely phenomenal and wonderful and beautiful presentation introduction. Very entertaining. And Dr. Hanna Roboczek-Helker, who joined me for this webinar. Thank you all who joined us, all viewers who joined us for this webinar. As I mentioned earlier, we had almost a full house, which is absolutely wonderful turnout. Now, what else can I say? Kościuszko Foundation is a membership organization. Therefore, if you are a member, that's wonderful. Thank you very much. If not, you are most welcome to join us as a member. Our next webinar is next week, May 18. And next time we are going to speak about Polish poetry. Jarosław Anders will be speaking about the poetry of Ewa Lipska, one of the most significant voices in the contemporary poetry from Poland. So if you have an interest in that subject, you are most welcome to join us. And now I wish you all a wonderful rest of the day, and we hope to welcome you soon.
I just want to say one more thing, that I am just so delighted that Dr. Iwaniec accepted our invitation, because he usually doesn't do that. So I was just so pleased on my behalf and on behalf of the Kościuszko Foundation and Piazza. Thank you very much.
I will speak to you, Anna.
It's not finished.
Please do.
At the end.
Okay, so it's about for us time to end this webinar. Once again, thank you all.
Thank you very much, very much. Thank you. Bye.